Hello everyone, today we will be presenting our work on interpretable image classification. So, over the past few years, deep learning models, especially the convolutional neural networks, have achieved remarkable accuracy in image classification tasks. However, despite this high performance, these models often behave like black boxes. In simple terms, they can give us very high accurate predictions, but it's difficult to understand why a particular decision was made. This lack of transparency becomes a serious issue in critical domains like healthcare, autonomous driving, and security systems, where trust and accountability are essential. Our project aims to address this problem. We focus not only on achieving high classification accuracy but also on providing meaningful explanations behind the model's prediction. So, in other words, our goal is to make AI systems more interpretable and trustworthy. But what is the exact problem we are trying to solve? So, the traditional image classification models simply output a label like cat or dog, but they do not explain which part of the image influenced that decision. This lack of interpretability makes it difficult for users to trust or validate the model. Our objective is to build a system that not only predicts the correct class but also highlights the important regions or features responsible for that prediction. By doing this, we can improve trust on AI systems, identify biases or potential errors, make the model more transparent and explainable. Now, coming to the methods, we didn't directly choose GradCam or PropNet because although they are popular, but they have certain limitations. GradCam provides us post hoc heat maps which are often coarse. They indicate where the model is focusing but not which specific feature it is using. Whereas the PropNet offers us a better interpretability through prototypes, but it introduces us to a higher architectural complexity and is harder to train and scale. The approach in our chosen paper, INTR, it provides us a better balance. It gives us more structured and meaningful explanations while keeping the model relatively simple and efficient.
Coming to the INTR idea, instead of extracting features first and adding class information at the end, INTR takes a proactive approach. It asks each class to search for itself in the image. Like instead of by example, like instead of one generic detective examining a crime scene, you have one detective per suspect. So formally for each class C, INTR extracts a class-specific feature vector from the image. That is the query. Then it asks, does the class C find itself in the image? The class C with the strongest TS wins. The class-specific search is what creates interpretability because each class has to actively look for its own patterns in the image. We can visualize exactly where it is loaded, and the map is the interpretation we get. So this is the uh, core inside. Like give the image, it passes through the encoder. It produces a feature map X, and through decoder, it runs class specific queries. Like in example ZN, we get painted bunting, and for each class, it searches for each class and give us output Z output for each class. The insight is like by making each class search for itself via cross attention, the attention weights directly reveal where the class was looking. So it directly helps in interpretation is no longer is an add-on. It falls out naturally from the classification rule. The new classification rules just comes out like y cap equal to argmax of w transpose dot g of phi, where g of phi takes f of theta feature map C and S, and it gives us class specific feature extraction via decoder. So continuing with the architecture, so it uses we have used a normal DTR model and later on changed the main decoder part by introducing specific class specific queries in the decoder part. The encoder parts take just an image input X and produces a feature maps. The main things like cross attention and multi-head cross attention is in the decoder part. So cross attention is a soft differentiable retrieval mechanism given a query vector Z and a pool of candidate vector X. Cross attention finds which candidates in the pool are most similar to the query and returns a weighted average of these candidates. Think, like given what I am looking for, pull out the relevant information from this collection. So in the INTR, the query is a class specific vector, what class C look like, and the pool is the image patches the visual content at special location. So cross attention is literally asking for this class, which special location in the image match what I expect to find. So later on, multi-head cross attentions come. In a single cross attention head can only look for one type of pattern at a time. Multi-head cross attention runs R independent heads in parallel, each with its own set of projection matrices, allowing the model to simultaneously attend to R different aspects of the image. This is what INTR ability to find multiple class attributes comes from. Uh, and head R has its own matrices. Each head independently computes its own attention distribution and the output features vectors. Then all R heads are combined. So one question, the main thing which distinguishes it, it's the W shared, and as W is equal to we our equation was Y equal to W transpose G of phi. So the differentiable factor is that W is shared. So uh, every to maximize the output in our training, if W is shared, then our model tries to find different features that truly makes the image different from one class to other rather than computing W. So uh, this is the differentiation factor that W is shared, not class. And then a question is one there, why INTR doesn't have the attention is not explanation problem. In standard models like BERT, attention in is one of many stages and downstream layers can compensate for uninformative attention. In INTR, the Z out equal to V dot alpha C and the logic W dot Z out. The attention weights directly and inclusively determines the downstream, which directly determines the logic. There is no downstream and upstream compensation possible. Manipulating the attention weights at inference time directly and proportionally changes the logic, which directly changes the prediction. So attention is the mechanism.
I'll be continuing from here. So, talking about our contribution in this paper, after reading this paper, all of us had the same thought or the same flaw in this paper, that is exactly one query vector per class. That's like a fixed point in d-dimensional space. So, so this is a information bottleneck because a single vector has to represent a class that could be in any way. It might be in purged, flight, or half hidden, or in various ways. And all of this has to be compressed in one vector, which is literally an information bottleneck. So our approach to it is that instead of exactly one query vector per class, we introduce k query per vector class. So let's see how that would change the architecture and the equation regarding it. So first of all, let's talk about the attention logic. In the original, this is the equation, and the problem with this is that rank of AC would remain attention logic would always remain one, no matter how deep the encoder is. It would all in terms of analogy, it would be like each class can ask only one question. That's quite limited. So what we try to do is um, in using k queries instead of one, this shoots up the attention logic to up to k, so it can ask k questions per image. So that would lead to much more accurate results. But one problem arises if there are k logics, but we only require one. So how would we compress k into one? So there are different methods to it. Let's explore why one would work, why one might not. So first, the obvious choice, that's taking mean of all the k vectors k logits, and this would not work because if you average k output vectors, you are blending k different signals into one that would not make sense, and the average of all these k output vectors would not point to any direction, would not lead to any strong signal that would appear in the class's direction. So that's like wasting all the efforts we uh, put in learning k vectors, and it would give us the same efficiency as rank 1. Second approach would be max aggregation. We compare all the scalar logic and, and take the maximum of it. That let's see how this practically turns out. So in this, k equal to 2, comparing mean and max. As you can see, mean is very blurred and not localized, and it is all over the place. That really doesn't give us a very strong suit on why one would classify this as a particular class. Whereas in max output, it is focused on particularly in these, and it would help the model in classifying further correctly. So, so we can see this in competition as well. This is the practical, like for a particular class like bunting, we would take multiple queries and compare and take the max of it. So in this case it would be 0.82, in this it would be 0.51. So this is how it would work in practical. One question arises that if If only the max one gets the gradient, wouldn't this cause the other k minus 1 vectors to collapse and get starved? But that's really a very wrong intuition, because this is based on an assumption that the same query would win all of the time for every image. That is clearly not true, because as the images are different, and different query would win, and these all k queries are in a competition, and they would as a result learn different k perspective about the particular class. So as a result, if any of the k query vectors would not collapse, and this answers the question. So to summarize our approach, it has four major properties. It has zero new parameters. We do not have to learn any extra parameters to further process this. Second of all, no unambiguous interpretation. If a particular class has one, this is because of a query vector k star, not because of any other k queries. So it has only one contributor in the winning of one class. And third point is structural diversity, and that is all the k vectors and does not copy of each other. Instead, they learn different perspective of each class and have a fierce competition among themselves to win. And fourth is hypothesis selection. That is, we take the best of that we take the k views of a class and take the one that fits the best, and then compare it to the maximum. So a model is committed to the best fitting view. That is exactly what a human would do as well.
So let's see the a demo of how our model is working. We have this yellow wobbler photo on screen, and then our INTR plus goes further with instead of one query per class, it takes k queries. Here we took k equal to 3, so yellow wobbler now has 3 independent query vectors, each free to specialize to different view of the bird. Coming to the demo part, we will be running this code, and there is k queries per class equal to 3. Model loads runs a single forward pass, no grad cam gradients, no rise making, nothing post hoc. Results class 182 yellow wobbler, probability with one nearly 1, perfect confidence. Next closest class gets around 8.78 e to the power minus 9, 9 orders of. Then let's move to these heat maps. JET color map. These show red and orange mean maximum attention. Blue means ignored. Look at the peak red orange region. It sits exactly on the wing body junction and mid back. The head and the beak light up in yellow region. The background. Sky leaves branches are completely blue. That is, they are ignored completely. Now switch to the raw scale. This is attention weights directly from the cross attention layer before any colorization. The bright white blob traces the exact silhouette of the bird. Nothing else. No leaf, no branch, no sky picture. This is what faithful attention means. The cross attention weights are the decision mechanism. The model predicted yellow wobbler because query 543 found the yellow body and wing streaks in the exact region. If you mask the region out, the confidence would collapse. That is what deletion score of 0.001 percentage when confirms. When you remove the attention patches, prediction drops to nearly zero immediately. So next, moving on to why k equal to 3 matters. We see q start equal to predicted star into k, that is 181 into 3, 543. Q end is equal to q start plus k, 543 plus 3 equal to 546. Here is where k equal to 3 actually matters in the code. We take all query logic from 543, 546, the 3 yellow wobbler hypothesis, and take the argmax. Query 543 wins offset 0 with original INTR at k equal to 1. There is only one query at index 181. That single vector has to represent every possible yellow wobbler, side profile, frontal view, partial occlusion, all compressed into one 256 dimensional point. This is the information bottleneck we identified. With k equal to 3, each query can specialize. Query 543 specialized to the lateral wing visible pose. Queries 544 and 545 would active for different views. The max aggregation selects whichever hypothesis fits the parent image best, and the faithfulness guarantee still holds. So next comes is the top 5 predictions. We can see in the JSON file. Finally, the top 5 prediction: yellow wobbler at 1.0, the ring kingfisher at 8.78 e to the power minus 9, and the other one at 2.94 e to the power minus 14. Notice the pattern. The run-up classes all are wobbler or similar colored small birds. The model's confusion is semantically meaningful. This is a property of class-specific search. The queries that are most similar to yellow wobbler queries are other wobbler queries because those classes share visual attributes. So on concluding, our model on a single pass gives the correct class with probability nearly equal to 1. Attention precisely on the bird, nothing else. No post hoc tricks. This is the INTR plus with k equal to 3. Interpretability, that is directly built into the model.